Hi, my name is Geoff Henshaw. I'm the founder and CTO at Aeroqual. My presentation today is entitled Reliable NO2 Measurements from Air Quality Sensor Networks. I'd like to start off by firstly acknowledging my co-workers, Anna Farquhar, David Bones and Lena Wissett from Aeroqual, and Professor David Williams from the University of Auckland. My talk today will be in essentially two components. Firstly, focusing on the sensor technology for measurement of NO2, and then secondly, looking at network calibration methods. The most common sensing technology for NO2 measurement is electrochemical gas sensors. And these are electrochemical cells in which the gas diffuses into the cell and reacts at the sensing electrode to generate a current. And it's the current that is measured in order to determine the NO2 concentration. Each of the cells usually contain about 3 electrodes. There's the working or sensing electrode in which the target gas reacts. There's a reference electrode and a counter electrode. And these are surrounded by an electrolyte, usually composed of sulfuric acid. The sensing electrode is usually coated with a catalyst to promote the sensing reaction. In the case of NO2, NO2 is reduced to NO, and simultaneously at the counter electrode there is the oxidation of water reaction. As I said, the output of the cell is a small current, and this is usually on the order of a few nanoamps for ppb levels of NO2. There's been a number of recent innovations. The first is a 4-pin version with an extra electrode called an auxiliary electrode that's not exposed to the gas, and this is used to compensate various temperature and perhaps humidity effects. And the second significant innovation is the development of ozone filters, which are usually located just between the inlet capillary and the sensing electrode. And this is to remove ozone cross interferences, a well-known interference for NO2 electrochemical sensors. The filters are usually composed of manganese dioxide material coated on a PTFE porous substrate. This slide shows some typical responses of NO2 electrochemical sensors when put into ambient air. The upper traces are from temperature recording in grey, dew point in red. The lower traces, the black dotted line is the reference analyzer. The orange line is a 3-pin NO2 sensor with an ozone filter. The blue line is a 4-pin NO2 sensor with an ozone filter. Two things are evident. Firstly, there's a number of fluctuations in the electrochemical sensor data that seem to correspond to changes in temperature and dew point. Secondly, that's not quite so clear, is that there are slow changes in the baseline pattern for the electrochemical sensors due to diurnal changes in temperature and dew point. So the question is, what are the causes of these drifts and transient spikes? What we have been able to do is to replicate those temperature and dew point behaviours in the laboratory. And in the top two graphs here, we have a graph on the left-hand side showing the baseline current in response to steady state temperature changes, and on the right-hand side, dew point changes. So these are these graphs are made by changing the temperature, waiting for the whole system to stabilize, and then measuring the baseline current. And you can see that there is a response to temperature changes and to dew point changes. And these effects are on the order of a few nanoamps above the baseline current. However, if you do a step change in either dew point or temperature, you can see a much larger transient effect. So the bottom two graphs show changes in the current in response to, firstly, a step change in temperature of only 7 degrees, and in the case on the right-hand side, a change in the dew point of about 2 degrees to 14 degrees. And you can note that the size of the currents generated by the transient behaviour are significantly larger, perhaps 10 times larger than the changes due to the steady state behaviour. And the question is why this might be. What's generating these very large transient currents? This next slide shows our hypothesis for these baseline signal changes. We believe that the baseline current is likely due to oxygen reduction in the sensing electrode. And this current will be sensitive to the wetted electrode area and electrolyte composition. The changes in that wetted area are due to movement of the meniscus, which is that three-phase boundary between the gas, the solid electrode and the electrolyte, would cause changes in the current. And this movement of the meniscus is likely to be driven by several factors, including changes in the interfacial tension at that interface due to changes in temperature or humidity, gradients of temperature or interfacial tension within the electrolyte, and or changes in the reference electrode potential. And this has recently been analysed in a paper by David Williams, currently out in Current Opinion in Electrochemistry. So how might we mitigate these effects? In the case of the steady state baseline changes, these are relatively easy to correct using a baseline algorithm which takes into account the temperature or humidity at the time of measurement and then applying a polynomial correction. But in the case of the transient noise, this is much more difficult because the signals are transient, short-term in nature. It's actually quite difficult to do that in software. And we've been looking at using sample conditioning materials with some success to address and minimise this transient behaviour. I now want to turn to the question of sensor network data validation. Aeroqual has been working with the University of Auckland over a number of years developing data validation techniques. And this work's been published in a number of journals shown here. I'll be presenting some of the work from the latest paper published this year in Atmospheric Environment concerning NO2 measurement. We've developed a network validation method called MOMA. It assumes that within the sensor network there are trusted reference instruments called proxies, and these might be fixed, mobile, or even calibrated non-reference instruments. The method derives slope and offset estimates by matching the statistical moments, such as mean and variance, of the sensor data distribution to those of the proxy distribution over the same time period. So as I said, these assumptions are that there is a reference instrument within the sensor network region and that the sensor outputs are linear. We developed these methods during the course of a sensor network project that ran from 2017 to 2019, in which we deployed about 100 sensors in the South Coast area of California. We did this when working with partners, South Coast AQMD, University of Auckland, but also community groups such as CCV and the Riverside Unified School District. This essentially became our laboratory for the development of these techniques. The MOMA method was developed and evaluated using AQI NO2 sensors co-located at 9 regulatory sites within the network, shown here in the graphs. The AQI sensors were corrected using proxy regulatory sites that were not the co-located stations. And the corrected AQI sensors were then evaluated against the co-located station data to give us an indication of how good the correction was. The first step in the MOMA process is to define the proxy stations for each of the co-located AQIs. NO2 has a high spatial variability, and so Proxy selection was based on land use similarity rather than the nearest regulatory site. 3 variables were selected based on a literature review of US land use regression models and also the availability of data. We chose distance to freeway, primary road length within 1 kilometre and elevation. And in the table to the right are the proxy selections for each of the regulatory sites. And you can see that in some cases the proxy is some distance away from the regulatory site. In this slide is a brief schematic of the MoMA correction framework. NO2 is calculated by the difference between the electrochemical sensor and the ozone sensor. So step 1 is to correct the ozone sensor. Step 2 is then to correct the NO2 sensor. We also ran a drift detection system automatically to decide whether or not a particular sensor should be corrected or not. So the process was to do the drift detection and then to calibrate when necessary. So this slide shows the results of the process. The monthly average mean absolute bias is presented here for both the framework corrected and the uncorrected. You can clearly see that the corrected had a much lower mean absolute bias between about 2 and 8 ppb versus the uncorrected of up to 20 ppb. So there's been a significant improvement. However, there is an outlier here in blue, the site at Compton, and I want to compare Compton with the one at Fontana in a bit more detail. I'm showing 2 different graphs here. On the left-hand side are the site distributions at Compton versus Fontana, and on the right-hand side you can see the time series data for the 2 sites. And what's clear is that the regulatory site distribution at Compton is very different to its NO2 proxy at Hudson, which results in the sensor NO2 correction overestimating the NO2 compared to the regulatory data in July. Whereas the regulatory site distribution at Fontana is similar to its proxy at SNBO, which results in the NO2 correlation being well correlated with the regulatory data. So this shows the importance of the requirement that the distribution of the proxy is similar to that of the site. Finally, if your sensor network is validated, you can begin to reveal the spatial variability of pollutant concentrations. And this shows some maps showing the mean diurnal NO2 variation in the Riverside San Bernardino area during July 2018. And it does reveal the inhomogeneity of NO2 over small spatial distances. So in conclusion, NO2 electrochemical sensors have been improved over the past few years, but they still exhibit transient responses which need to be taken into account when looking at the data. We've developed an NO2 sensor management framework called MoMA, and it has been successfully tested in California. What's clear is the selection of suitable NO2 proxies based on land use is better than closest proximity, but it's still challenging due to high spatial variability of NO2. And finally, a dense sensor network, when managed correctly, can provide reliable information about local sources and dispersion of NO2. Thank you for your time.